Good afternoon. My name is Jill Salamanca,
I'm Colby Levine.
I'm John Caroline.
I'm Jonathan Ciasia.
and today we are going to discuss natural fractures. To understand how natural fractures affect reservoir conditions, we first need to understand what they are and how they are formed. So what are natural fractures exactly? Natural fractures are breaks in the matrix of the rock. They are caused by various stresses that occur on the rock. Shear stress situations occur at faults. Compression can occur due to the overburden stress on the rock, and tensile usually occurs when there's cooling or shrinking. Natural fractures are important to understand because they can assist or diminish the production of hydrocarbons. Also, most reservoirs contain natural fractures, so new reservoirs are usually assumed to have natural fractures until data proves otherwise. Now, John is going to discuss detecting natural fractures using various tools.
Equally important as understanding how fractures affect our reservoir is understanding how to detect them. There are a variety of techniques used to detect natural fractures through log and core analysis. The primary logging tool for identifying fractures in reservoirs is the reservoir imaging tool. For example, Halliburton's XMRI, the Extended Range Microimaging Logging Tool, uses a contrast resistivity image to give a fracture image, dip of the formation, and high-low resistivity delineation. The Formation Microscanner imaging tool gives us a detailed image of the borehole wall, which assists in gathering formation information. Reservoir imaging tools alone are unable to characterize fracture networks properly. Therefore, dipole sonic logs are also run. The sonic tool propagates shear waves through the formation with different velocities in different directions, called acoustic anisotropy. The different relationships between these shear waves and their travel velocities and paths help us identify the rock anisotropy mechanism. The homogeneous anisotropic relationship, as can be seen on the following graph, is an indication of a fracture. For a more physical representation of a fracture, we also pull cores from the reservoir. Fractures can be seen very easily in a core sample, but some cores can be damaged during extraction. Therefore, it is important to identify the difference between them. Here, as you can see in this picture, we can clearly see the difference between a natural fracture and a damaged core. The picture on the left is a natural fracture, and the picture on the right was a core that was potentially dropped during extraction. A common experiment for cores used to determine if there are any fractures that we cannot see by the naked eye is the test represented here. On the right, water is first pumped through the core diagonally, then vertically through the top and the bottom of the cylindrical core. If no fractures are present, the horizontal flow should be greater than the vertical flow due to layering and striations in the formation.
The image shown is both a 3D and 2D projection of the immediate wellbore vicinity, produced by Formation Microscanner. As previously mentioned, the Formation Microscanner produces an image of the wellbore based on its resistive and conductive properties. This technique, paired with an acoustic image from a sonic log, gives us a very effective method of detecting fractures in the formation. Fractures and formation dips are clearly represented in this diagram produced by the Formation Microscanner, which are marked on the right chart.
Now let's take a look at how fractures can affect permeability. Given this certain core sample, we can calculate the porosity of the fracture. Plugging these numbers in, we get a porosity value of 0.83%. That's a pretty low porosity. Let's go and calculate our intrinsic permeabilities. The intrinsic permeability of the first fracture is 5.4 times 10 to the 6 millidarcy. And the intrinsic permeability of the second fracture is 21.7 times 10 to the 6 millidarcy. Lastly, we'll calculate our bulk permeability. Plugging the three numbers we had just calculated, we get a bulk permeability of 13,600 millidarcy. This is an extremely high permeability. To conclude, we see that even though our core sample has a low porosity, the fractures have provided a high permeability. This means that a fractured rock allows more flow. Now, in some cases, the effect of fracture aperture can improve production, but in other cases, it can complicate producing the reservoir. Let's take a look at the cubic law and how it relates to fracture aperture. When looking at this equation, we are assuming that the two fracture walls are parallel and smooth. Therefore, we would consider this an ideal fracture. But realistically, the fracture walls may be in contact in some areas, and the walls would be rough. Nonetheless, we can still use this equation to see how aperture affects flow. Q is our flow rate, rho is density of the liquid, G is gravity, mu is viscosity, B is the aperture or width of the fracture, little h is the hydraulic gradient, and big H is the height of the fracture walls. As we increase B, Q will also increase exponentially. If we decrease B, Q will decrease exponentially. Therefore, we can see how the width of the fracture has a direct relationship on our flow rate.
Natural fractures can be both friend and foe when it comes to economically producing a reservoir. They're known to shorten the overall lifespan of the well, but have a higher initial production rate than assumed initially. Here are a few challenges generally faced when dealing with natural fractures. Over time, as you deplete a well, the pore pressure or the fracture pressure inside of it itself will decrease. That closure stress that's always acting on the reservoir stays the same. So once the point arrives where the fracture pressure is the same as the closure pressure, that's the point that the fracture begins to close itself. Once that closure pressure exceeds the pressure inside of the fracture, then it'll close the fracture. And if that fracture just so happened to be the only means of permeability that you had in the reservoir, which does exist in some rare occasions, then you no longer have flow. So that well's dead. You also have situations where, when drilling, you may make fractures parallel to the wellbore. Now, this can arise an issue when it comes to production because if you're not in that deep of a well, these fractures are known to stretch long distances, so they can actually reach the water table. And it may be good and look like you're overproducing at first, but that's because the water table is actually leaking down into your wellbore and you start producing more water as well. You also have situations when it comes to tortuosity in the wellbore. Fractures are formed by forces beyond our control. They have max stresses and minimum stresses. The fractures usually form parallel with the maximum stresses, perpendicular to the minimum stress that acts on the matrix. And when these fractures have a direction, basically, we may drill the wellbore and start producing it and notice that we're not getting as much as we thought we would, or something along those lines. And that could be because of a situation like this. If you have a very tortuous wellbore, then you may not have as smooth of a flow throughout the wellbore as you would like. So it's good to know that you have fractures present in the direction that they run before you initially drill in order to know how it's going to produce later on.
To summarize what we just discussed, natural fractures are important to understand because the aperture affects permeability and flow. There are many different tools that are available to detect fractures downhole. Even though natural fractures are helpful to production, they can also be challenging and may be hindering. Thank you for your time, and I hope you enjoyed our presentation.